Okay, so we have homework due Wednesday. I am going to add some more to that from what I put up so far. So that'll be due Wednesday in lecture. And then after Thanksgiving, we have one full week, 3 more days, and of class. And you have the post. You have 2 exams that week. You have the post test Tuesday or Wednesday, and that's very similar to the pre-test in terms of length and what it's like. So you'll take the post test Tuesday and Wednesday, and then we have exam 3 Thursday. So before Thanksgiving break, I'll put up all your review materials for exam 3. Okay, any questions on that? And then the week after that is finals week, and we have our final Tuesday night. So it's a week from, 2 weeks from tomorrow night is our final exam. Yeah. It'll be similar to the first post. The pre-test was extra credit on exam 1. The post-test, depending on your performance, will be extra credit on exam 3. So you can earn some bonus on exam 3. It's a required element. Again, if you don't take it, then you don't get your score for exam 3. And then depending on how you do, you can have a little bonus on exam 3. Other questions? Okay, so here's where we left off. This is a summary of last class. So could you fill in this table without your notes from last time? So do you remember what the meanings of input and output are for arc sine and arc cosine? And then what are all possibilities for the inputs and all possibilities for the outputs? So take a minute, talk through these with the person next to you without looking at your notes. See if you remember. And the pictures down below can help conjure your memory. Okay? Go. Okay, Zach, you're up. Tell me what the meaning of the input into arc sine is. Distance from the y-axis. In what unit? Radius length. So he wants distance from the y-axis and radius lengths. Do you agree with that?
The right.
What's that?
To the right.
Distance to the right.
No. Everything he said plus to the right.
Okay, so distance to the right of the y-axis and radius lengths is arc sine. The input into arc sine. Taylor.
The vertical distance above the horizontal plane.
Okay, in what unit?
In
Radius lengths. Okay? It's vertical distance, right? Because the output of sine is vertical distance from the x-axis, or the horizontal diameter. Okay, that's also the y-coordinate on the unit circle, or the y-coordinate in radius lengths. Okay, so what are all possibilities for the number of radius lengths above or below the horizontal diameter? What are all possibilities? Jonathan? From what to what? Right, the furthest down we can go is 1 radius length on the circle. You can't go any lower than 1 radius length below, and the highest you can go up is 1 radius length up at the top of the circle. Okay, what's the output of arc sine? Malenko. Angle swept counterclockwise from 3 o'clock. That's right. Okay, and what are a range of outputs? Remember, we had to restrict this, so we just got 1 angle for every vertical distance that we picked. We just want to get one angle, so we restricted it to what?
Negative pi over 2 to pi over 2.
Yeah, so looking down here, if we pick a y coordinate or pick a vertical distance, if our angles are from negative pi over 2 to pi over 2, then we get just one angle for every value y coordinate from negative 1 to 1. Okay, input meaning of arc cosine. Somebody knew. Naz.
Horizontal distance from that vertical diameter
Okay.
and right and radius length.
Okay. Or what else could we say it is? What coordinate?
Oh, it's
X coordinate, right? So it could be the x coordinate or the horizontal distance, right? Or the vertical diameter in radius lengths. What are our possibilities for that? Patrick, what are all possibilities for the horizontal distance right of the vertical diameter? Yeah, so the furthest we can go to the left is 1 radius length, and the furthest we can go to the right is 1 radius length. Same as the output of cosine. Same as the output of cosine, okay? What about the meaning of the output of arc cosine? Frank? Yep. And what are the possibilities for that? If we want to hit every x coordinate from negative 1 to 1, then what range of angles gives us just one angle for every one of those? 0 to pi, the top of the circle there, 0 to pi. So when you're using, so it's really, this is critical, when you're using inverse sine and inverse cosine on your calculator and you get a number, you have to know what that number means to apply it to your problem, whatever your problem is, because it's not just as simple as taking that number and that's your answer, okay? So you really have to know the input and the output, and especially these, why you get the number that you do in terms of within that range of angles, either negative pi over 2 to pi over 2 for arc sine, or 0 to pi for arc cosine. Questions on this summary, review? So we're going to do one more problem, and then we'll do one more problem that uses this stuff. And then you've got more for your homework. Can I move from this screen? Any questions? Okay, so we've got a remote control car. Drives around a circle of radius 8.5 feet. So here's our radius, 8.5 feet. And we've got this remote control car that can drive around in a circle. So before we start, we've got to decide what car we want. Very important. So do we want the Formula One?
Yes.
Or the Lamborghini? Which one do we want? Or what about the monster truck? Oh, maybe not the monster truck. All right, so which one should it be? I hear lots of Lamborghinis. So let's do Lamborghini. Oh no. Oh, come here. Here it is. Okay, there it is. All right, so it's going to start at the 3 o'clock position. All right, so it starts at the 3 o'clock position. And so it's going to go, it makes it almost all the way around, and then it runs out of juice at 6 feet to the right of the horizontal diameter. So that's 6 feet right there. So the question is, how far did it go? What distance around the arc did it travel if it ended up 6 feet to the right of the vertical diameter? Okay, so we need, this isn't a simple thing. This takes some steps, some different, we need a roadmap, or we need a strategy here. So we've got this 6 feet to the right of the the vertical diameter, and we need to find arc length. So, suggestions for a strategy? Yeah, Jackson. Okay, so why? So that's kind of like the first step, but let's talk about the overall big picture of solving this. So do you have something in mind for how we're going to do this?
Yes,
Tell me.
You're going to convert that into radius lengths, punch that into arc sine, because you're going backwards to try and find the angle. Once you do that, it's going to punch out wherever it is, because it's what is that, 6 feet still.
So let me just stop you. So no, everything you're saying is right. So how does angle relate to what we need? So do you see, when you were thinking about this, did you think, oh, I want to get the angle? Does that help to get the distance traveled? Yeah, you should. That should be second nature, because that's just a very simple transfer of angle to arc length, because that's what radians is, right? Radians is arc length in what? Radius lengths, right? So if we had this angle, we could get the arc length no problem, right? It would just be one more simple step, okay? Because we understand what radians are. So how are we going to get that angle? So you want to get that angle through arc sine. What do we think? He changed his mind. Arc cosine. Which one? Arc sine or arc cosine? Arc cosine takes what and gives what?
Takes the angle right of the vertical diameter, distance and radius. Right.
It takes what and it gives what? So arc cosine, what's the input into arc cosine? That's why we reviewed it. Horizontal distance in radius lengths. And will give us what? Angle. Swept counterclockwise. Dot, dot, dot. So, we're going to put 6 into arc cosine. Is that right? No, we need... Right, so what arc cosine takes is radius lengths. So how many radius lengths to the right are we? So you should all know how to get radius lengths out of 6 feet. You would take 6 over 8.5 would give us the number of radius lengths that we are to the right. Okay, and so if you do that, everyone do that in your calculator. So we make sure you know how to do this. So it's second cosine, and then parentheses 6 over 8.5. And you should get 0.787. But make sure you can do it. Okay, so I want you to tell the person next to you, what does that number mean? That number you just found relative to our situation. What is that number? See if you can figure out what that number is. Is it the angle that we need? Is it a different angle? What is it? Go. Okay, Michelle, what do you think? That number 0.787, how does it relate to our situation? So is it if it was swept clockwise, it would be a negative value, so it's positive. So it's a counterclockwise angle. Is it our angle? So what if it's not our angle? Then what angle is it? What are you looking at there, Angelica? Our percentage, so like 78%. Is this 78%? So it is. You're saying it is this angle, but it's as a percent of the whole circle. What do we think? Adam says no. Adam, what do you think? You really don't know. So it goes back to. So any volunteers? What does the 0.787 mean? Somebody knew. Fernando.
It's the percent of 2 pi that gives us the
No, it's not a percent of 2 pi. So why did we go over this? What are the possible outputs? Possible outputs are what? 0 to pi. Possible outputs of our cosine are from 0 to pi. So when you put that in your calculator, where does your calculator think that the car is? Does it think it's there? Where does it think it is, Scott?
It thinks it's at 0.78 of 1 radius around the circle counterclockwise.
So where? Tell me where that is. Where?
It's going to be reflected over the x-axis on the plane. I'm not sure.
So where does it think the car is? He thinks it's reflected over the x-axis. Pi over 4. It thinks it's here. It's got to be. It's the angle, or it's the location from 0 to pi that's also 6 feet. It thinks it's here. Because the output of our cosine is only from 0 to pi. So it thinks the car is there. And so do you see what angle it gave you? Can you imagine what angle it gave you? Yeah, Adam. This is, your calculator doesn't give you a percent. Your calculator doesn't give percent. What is this number? What is the units on this number? This is radians. This is radians. So what angle did it give us relative to what we're looking at here? Aiden.
It's the angle that the car would have to keep going to complete the whole circle. It's like the rest of the circle.
This 0.787?
Yeah.
No.
If it were to go another 0.787, it would end up at 2 pi.
No, it's an angle. That's not right. It's an angle. It's some angle between 0 and 2 pi such that the horizontal distance is this number of radius lengths, or 6 feet. So what angle is it? Naz?
Isn't it supposed to be the one opposite? Opposite of the car?
Yeah, it's just the angle between 0 and pi that takes us to that spot. That angle right there. That's 0.787 radians. So when you put that number of radius lengths into our cosine, it's going to find the one angle between 0 and pi that gives you that number of radius lengths. And that was 0.787 radians. Doesn't make sense. So that's why you really have to understand what's going on when you use inverse sine and inverse cosine in your calculator. You got to know what that number means relative to your situation. Okay, so now how can we find, we want the red angle. So we've got that blue angle, we need the red angle. What's that? Negative 0.787 is the red angle. What do you think? Dustin?
Well, that's one way. You also do 2 pi minus the 0.787.
So our angle is 2 pi, a full rotation. Yeah, so a lot of you are seeing that that's the same angle, that's the same amount of openness as 0.787. So if we went 2 pi and then minus 0.787, and what do you got? Put that in your calculator. 5.50. And what's the units on that number? Radians. That's our angle in radians. And now we're home free, and we can get this distance if we understand what a radian is. So how do we get that distance in feet if this angle is 5.50 radians? Somebody knew. Yeah, Scott.
Multiplied by 8.5,
And why would you do that?
because that's the radius line, so you just convert it back to the original measurement.
Yep, so that amount of openness is the amount of openness that its rays would cut 5.50 radius lengths. So 1, 2, 3, 4, 5.5 radius lengths would be a total of
46.71 feet.
40. Say it again, what'd you say?
I got 46.71.
46.7 feet. Okay, questions? Doesn't make sense. So these get this. There's lots of situations that you can be given, and especially down here in these bottom two quadrants is where it gets trickier, and you really have to know when you use that inverse sine and cosine. It goes back to that first chart. Exactly what output are you getting? What angle are you getting relative to your situation? And then you often need to make an adjustment. Questions on that? Doesn't make sense. Okay, so you'll have similar questions in your homework. I'm going to use the same diagram, but kind of show you something new. Can I erase what's on the screen? Okay, here we go. So now I want come on. No. There. Okay, so now the car is 4 feet to the right. So now this is 4 feet to the right of the horizontal diameter. Okay, so find the angle. Just as a practice, find the arc length that the car has gone from the 3 o'clock position. See if you can do that. So find the arc length that the car has gone from the 3 o'clock position. Yeah.
If the car's in the first part, you use either one part of the time on the stage.
Okay, so he's asking, with the given information, can you use either one, arc cosine or arc sine in the first quadrant? What do you think? What's the input into each of those functions? What's the input into arc sine? Input into arc sine is vertical distance and radius length. So you could find that, but you don't have it. So you're going to use arc cosine. Okay? So arc cosine of 4 over. I'll write it this way this time. Anybody get a result for that? 1.08. Okay, and so how far did it go? So what is that? 1.08. What does that mean? That's the radians. Is that the angle, the true angle of where our car is? Yeah, because that is between 0 and pi. So that's exactly where that is, 1.08, because of the output of our cosines between 0 and pi. So then we can take 1.08 times 8.5 and we get? So we've gone 9.1 feet. Okay, so no adjustment on that one because we were in the first quadrant, and that's the first quadrant from 0 to pi over 2 is part of our range for our cosine from 0 to pi. Okay, so can you imagine that me representing that distance on the x-axis. So that distance of 4 feet. Can you imagine what it would be like if I represented it on the x-axis? So you should all have an image of what that is. And so is this what you were thinking? So I just took that distance and I just moved it down here. So this is 4 feet. Okay, and then I could likewise put the vertical distance above the horizontal diameter right there. What's this distance right here? From the origin to the car. Why 8.5? Yeah, it's still a radius, right? At 3 o'clock isn't the only place where the radius is, right? The radius is everywhere from the center to any point on the circle is the radius 8.5. Okay, so now I want you to, we already did this, but what's the number of radius lengths to the right that the car is? I want to represent that. Number of radius lengths. Right of the vertical diameter. How would you represent that number of radii right of the vertical diameter? Ryan. He said 4 divided by 8.5. Okay, so the number of radii to the right of the vertical diameter. Well, that should sound familiar. We have another way of expressing that. The number of radii, or the number of radius lengths to the right of the vertical diameter. What is that? Got it? What's that? He said sine. Arc sine. Is it sine or arc sine? Just cosine. Arc cosine. We got all 4. So which one is it? We got sine, arc sine, cosine, and arc cosine. Which one of those gives, or its result is, the number of radii to the right of vertical diameter? We should all know this. We should all know this. It's cosine. The output of cosine is the number of radius lengths to the right of the vertical diameter. Cosine of what? Cosine of theta, right? Okay, so that ratio, 4 over 8.5, is the cosine of theta because it gives us the number of radius lengths to the right of the vertical diameter. Now look, we made a right triangle here. So the right triangle has 2 legs. One of those legs is one of the sides, or is next to, the angle theta. And the other leg is across from, or opposite. Okay, so this leg that's next to, another word for next to is adjacent. So that's the adjacent leg. All right, and then there's 2 legs, right, that make up the right angle. Then this leg is called the opposite leg. And then what's this called in a right triangle? Hypotenuse. It's not a leg, it's the hypotenuse. 2 legs and a hypotenuse. Okay? 2 legs and a hypotenuse. So this cosine theta as the 4 over 8.5, then, as the number of radius lengths to the right of the vertical diameter, could also be written as the adjacent leg, that 4. I'll write it up here. So the adjacent leg, and the 8.5 in that triangle is hypotenuse. So many of you have heard that before, you've used that before, and that was probably, for some of you, it might have been all you knew that cosine was. But what I want to point out, that this ratio of the adjacent side to the hypotenuse is the number of radius lengths to the right of the vertical diameter. That's why it's cosine. That's why it's cosine, because it's giving you that fraction of a radius that we are to the right, like we've been talking about for the last 2-3 weeks. So now we're just setting up that same ratio, but we've got names for these lengths in the triangle to get that same ratio of a fraction of a radius length that we are to the right of the vertical diameter. Okay, so it turns out that this side, how could you find this side right now? Could you find that side?
7.5.
How'd you get it?
I use a squared plus b squared equals c squared.
Yeah, so we could do 4 squared plus b squared equals 8.5 squared. That's Pythagorean theorem, and if you solve that out, you get 7.5. So, what's the number of radii above the horizontal diameter? No, give me yeah, that's true. But give me the in this particular triangle, how could you calculate that? Could you express it? What is it?
7.5.
Yeah, so it's going to be that number of feet, but we need to make it radius lengths. So it's going to be that fraction, 7.5, the fraction that 7.5 is of 8.5. Okay? And we know that what is the number of radii above the horizontal diameter? You had a sine. This is sine, right? This is exactly what sine gives. And in the triangle, what is 7.5? Opposite. And what is the hypotenuse? So these right triangle trig rules, so we're moving towards triangles, okay? So these triangle rules for sine and cosine, what I'm trying to say is those ratios are still giving the number of radii either above the horizontal diameter, that's sine, or to the right of the vertical diameter, that's cosine. So those ratios still come from the fact that we're measuring distances, right, in radius lengths. So what I want you to do is go to page 325. Okay, what you're doing on page, once you get there, everyone there? On page 325, they have you create circles that contain these triangles. So on the vertex B is always the center of the circle. So what is the radius of the circle? Which length of the triangle will be the radius of those circles? BA or BC? BA. Okay, now here's a common mistake students make. BC, is that a radius of the circle or not? Is it shorter or longer than the radius? BC is shorter. It's a fraction of the radius, okay? So don't try to draw your circle through A and C, right? BC is shorter than the radius, which is BA. The radius is BA. So you're drawing those circles, and then you're answering the questions, and you can go all the way through number 2, which is top of the next page. How'd these go? The first page should have been pretty straightforward based on what we did before. Any questions on that first page? So now what happens with this is, say you have a different orientation where that angle isn't our traditional angle swept counterclockwise from the 3 o'clock position. All right, well, watch. So this is really just a reflection of that angle that we're used to. Okay? The one we're used to would be something like this. So I could redraw that triangle like this, right? And then it's just a reflection, so everything's the same. This is theta. This is 10.6. This is 6.6. And this is 6.3, 8.3. So cosine of the angle is number of radii to the right of the vertical diameter. So it relates to this number. So it's the fraction of 8 that 8.3 is of the radius. And so what is 8.3? Which side is that? Adjacent to the angle. That's the adjacent leg. And 10.6 the hypotenuse. But so notice over here in the triangle we were given, it's the same thing. You've got the 2 legs. AB and BC are your 2 legs. The adjacent leg is the 8.3. And the hypotenuse, or the radius of the implied circle, is 10.6. So even when you do a mirror image, these relationships, adjacent, hypotenuse, and opposite, the relationships still hold to meaning the cosine, or the sine. So sine theta is the number of radius lengths above the horizontal diameter. So we can think of that over here. A circle like this. Okay, so sine of theta is number of radius lengths above the horizontal diameter. So how would we get the number of radius lengths above the horizontal diameter? 6.6 over the radius gives the fraction of the radius that 6.6 is, or the number of radius lengths. Okay, and so in this triangle, what's the 6.6 relative to theta? It's opposite. It's the opposite leg. And what's 10.6? Hypotenuse. So it's the same relationship that we had before. So these relationships always hold for cosine and sine. So now let's find that angle theta. How can we actually get that angle theta in either radians or degrees? What do we need to get that? Because this ratio isn't the angle, it's the cosine of the angle, or it's the horizontal distance right of the vertical diameter. Yeah, so if we've got our way now of getting, having that distance, so theta equals inverse cosine, we're going to put in 8.3 over 10.6, but then we have to make sure that we've got the right angle. So put that in your, let's do degrees now. So set your calculator to degrees first, and then do this calculation. The arc cosine, or the cosine inverse of 8.3 over 10.6. As soon as you get something, shout it out. 38.5 degrees. So now, do we need to make an adjustment or not? Or is that the angle, truly the angle theta? So we took 8.3 over 10.6 to get that horizontal length and radius lengths, and it gave us 38.5. Is that theta or not? They're saying no. But what's the output? The range of outputs for cosine inverse is from what to what? So in degrees, it'd be 0 to 180. So if our angle theta is already in that range to start with, then that's what it is. So there's no adjustment to be made. Does that make sense? The one that we had was outside our starting angle for the car was in the fourth quadrant, and so it was outside of this range that arc cosine gives. But since theta is in the first quadrant, that's what it is. And so then, because the relationships hold, then this is 38.52. So that the original angle there, 38.5. If we do the arc sine, we ought to get the same thing. So if we do the inverse sine of the vertical distance and radius lengths, or opposite over hypotenuse, you get the exact same number. And this is because we're thinking about this triangle in the first quadrant, and that first quadrant is part of the output of both those, the arc cosine and the arc sine. Because arc sine is from negative pi over 2 to pi over 2, arc cosine is from 0 to pi. So anything in the first quadrant, both are going to give you the right angle. And then that whole thing is just reflected into this triangle here that we were originally given. Okay, so look over on the next page. Page 327. So what about that angle alpha? So now we're really, when we look at alpha, that's quite a bit far removed from our angle, swept counterclockwise from the 3 o'clock position. But we saw that these relationships for sine and cosine still hold. No matter how we turn or reflect or maneuver a triangle, it should still hold. So what will the sine of alpha be? Sine of alpha should equal, so this is 2 centimeters here, and this is 6 centimeters here. We could easily find this. It would be the square root of 2 squared plus 6 squared, which is square root of 40. Because we have a right triangle. So what is the sine of alpha? It's our opposite over hypotenuse. Or? So now it's opposite, so whatever angle it's the sine of. So the opposite angle is, or the opposite side to the angle alpha is the 6. And the hypotenuse is radical 40. Yeah, question?
We don't need to rationalize the denominator.
We're just getting the ideas here. So, yeah, it's less important. Can we still, even though this is not the angle swept counterclockwise from 3 o'clock, can we still see it that way? So how can we see that angle as the angle swept counterclockwise from 3 o'clock? Does anybody, do you know how you can kind of rearrange your perspective to see that as our standard angle? What would you do? Jonathan? Okay. Okay, and where would my x-axis be going? X-axis go this way? Down. So if you imagine the x-axis here and the y-axis here, then does opposite over hypotenuse give us the number of radius lengths above the horizontal diameter? Yeah, because you'd be 6 would be now, this would be like up, would be this way, above. And then our radius would be the radical 40. So it still holds. It still holds. If you just imagine the x-axis that way, y-axis that way. Okay, homework due Wednesday, and I'm going to add a few more this afternoon.